Hello Squids, this is Squeevy here with another video. In this video I'm going to be going over organic chemistry. Now I usually do computer science, but I've decided, because I'm taking an organic class right now, I thought, yeah, it'd be pretty cool if I were to quickly do an organic video. So in this video we're going to be covering things like bond line notation, constitutional isomers, and formal charge. We're not going to get into hydrogen deficiency, that's going to be in the next video. But yeah, so let's get started. So if we do this, you should be familiar with Lewis dot structure. So suppose we were given CH3 or methyl. We could, there's really only so much you can draw for methyl. It looks something kind of like this. So this is just a quick recap. So you have to have an octet. So you have 2, 4, 6. 8. That is your Lewis bond structure for methyl. You should be familiar with that. That's a pretty elementary concept when it comes to organic chemistry. In fact, we use that quite a lot. Right. So the thing with bond line notation that you should know is that it's in a line of carbons. You'll see what I mean by that in a second. And it's zigzag. Those are the two basic rules of bond line notation. Those are the two basic rules of bond line notation. That's just something you should know. So, ooh. Which one did I have? I think I had this one. Nope, I most definitely had this one. So, make sure you know that. That is, like, really, really, really useful and what you should abide by. So, sorry if this video is a little choppy. I suck at explaining things. But, anyways, let's continue. So, in organic chemistry, you'll see a lot of structures that have, something that looks kind of like, this, something that looks kind of like, something that looks kind of like that. This is just an example, but you'll get something that looks a lot like that. A lot of times, with the weird line zigzag thing. What we're going to do is we're basically going to do that, and that's the absolute basics of organic chemistry. Like, when you go into organic chemistry, other than review, that is the first thing you'll do is bond line. So suppose we were given something like C5H10. Actually, I'm not, just C5H12. Suppose you were given something that looks kind of like that. How would you draw this? Well, if we did the Lewis bond structure of 1, 2, 3, 4, 5, and I'm just gonna put in these. I'm not gonna draw in the. Actually, yeah, I will, because when we're working with bond line, it's kind of confusing. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You literally just put in the hydrogens. Right? So I'm not going to be drawing in the hydrogens each time. It's not a good habit, and I recommend you draw the hydrogens each time. It's just really time-consuming to always be drawing the hydrogens. So you'd end up with something that looks kind of like this, right? Now, one thing you have to know is that carbons connect to carbons to form a line, and hydrogens you just don't draw in. So this would look something like 1, 2, 5. 1, 2, 3, 4, 5. It looks something kind of like that. This would look like that in bond line. Yeah, it looked like this in bond line. So, pretty much what I did here is each carbon is a little dot on the line. And the lines connect the carbons. Alright? So that is this in bond line. Bond line is really basic, and I'm trying to make this actually worth time and stuff, but it's really difficult to make this worth time. Now, so suppose, we'll get into this later, but you could also draw this as a ring, right? 1, 2, 3, 4, 5. Get a pentagon. It looked like that. Oh, actually, let me just make sure it does. 1, 2, 3, 4, 5. Yep, it looked like that. This is the same as this, right? So C5H12 is this in Lewis bond, this in bond structure, same thing. Now, how can you tell? So the ring is different from the bond. Here's why, or from the line. Here's why. Because here we have 12 carbons. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Where did the other hydrogen go? You can't draw this like this if you don't have any, if you have a full arrangement. You need a hydrogen deficiency to draw this. So this cannot be drawn like this. Yeah. So, now that we've covered that, I want to go over how do you draw double bonds. So suppose we were given this, say, right? 1, 2, 3, 4. 1, 2, 3, 4. Right here in the center, you just draw that. That's a double bond. Now, triple bonds. These are a little more tricky. These it's just a weird way of thinking with triple bonds. 1, 2, 3, 4. Right? 1, 2, 3, 4. That is what a triple bond looks like. It's always straight. So you have 1, 2, 3, 4. You can see how it bonded. In fact, this would be more up here, but that is how you draw a triple bond in organic. Alright, so if you could pause the video, I'm going to give you a quick exercise. How many hydrogens, and I'm actually going to work this one with you, and then you can, work a few more on your own. How many hydrogens are in this benzene? Now, what a lot of you may think if you haven't done much chemistry is, okay, there's 2 there, and the same throughout, so you have 10. But no, if you have this here, 2, 4, 6, 8, 10, you exceed the octet. You cannot exceed the octet. So what you have to do is get rid of this. It would just be like that and that. So you have 2, 4, 6, 8. You have an octet. It just keep coming off like this. So you'd really only have 1, 2, 3, 4, 5, 6. You only have 6 hydrogens there. Now, what I want you to do is tell me how many hydrogens are in, oh, no, I want that to be a bit of a bigger brush. How many hydrogens are in this molecule? So pause the video and do that. 3, 2, 1. Now you should have paused the video and done this. So now let's look at this. So we have 2 hydrogens there because that's the octet, and you cannot go lower than an octet, so you can't just have 1 there and then not much anywhere else. It'll be 1, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. This is tricky. 2, 4, 6, 8. No hydrogens there. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. So if we count this up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You have 13 hydrogens there. Alright? So, now, unbelievable. How do I clear? Clear, 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 clear. I'm... What? There's no clear? Fine. Unbelievable. Oh, I could have just done this all along. Look at that. So let's clear up a bit of room for formal charge. Okay, so now we have room for formal charge. So, let's look at a molecule that looks kind of like... Oh. Hold on. Let's do methyl. Let's find the formal charge of methyl. So it's either going to be 1, 0, or -1. Right? So, alright, let's start by drawing some Lewis dot structures, and then draw it in bond line. This is a bit different than how I drew it in the demo, but it looks like that. And then that, I don't actually want to draw an arrow because that would symbolize reaction, would turn into something that looks kind of like that. So the first thing we gotta do is find our carbon. So we want to find the formal charge on every carbon, but we can see we only have 1 carbon here. So what we want to do is we want to count out how many there is here. Now first, 2, 4, 6, 8. So we know that this has 2 dots here. Right? So we have 2, 3, 4, 5. Carbon has 6. So it's going to be a formal charge of 1. Now I went by that kind of quickly and I'm going to go over it right now. How did we get 1? So the first thing we got to know is each double bond, or no, each bond is going to represent 1. Now if it's a double bond, it's 2, because each bond is broken in half. So you only count 1 electron. And then here's 2 electrons, so it'd be 2, 3, 4, 5. That'd be 5. Now, how many valence electrons does carbon have? And the answer is 6. So it'd be 6 minus 5 is equal to 1. That's your formal charge. So let's look at something a little more complicated. Suppose we had this. No. Excuse my drawing. It's ooh, that is quite the most awful thing I've ever seen in my entire life. I can draw, right? Right. So we know something looks kind of like this. Now, nitrogen. Let me pull up a periodic table. Periodic table. Just let it load. Right, so we have nitrogen, and we want to find out how many valence electrons it has, and all that stuff, right? So 2, 4, 6, 8. Right? So let's just put that in there, just to make this a little less confusing. Actually, yeah, because then this has a hydrogen deficiency, and I'll go into that later. So suppose we have this. Actually, you know what? No. Let's just keep it like that. Okay? Let's go to images. Hold on. Itchy. Itchy, itchy, itchy. Oh my goodness. Well, I'll let it behave. So we know you have 1, 2, 3, 4. So that's going to be. Oh, that can't be right because nitrogen is like. Nitrogen, nitrogen, nitrogen. Oh, okay. It has 5. So yeah. All right. So we have 1, 2, 3, 4. Right? So it's going to be 5 minus 4 is equal to 1. There you go. Give yourself a pat on the back. Now, let's do something a little more complicated. Find the formal charge of the oxygen on this molecule. You can pull up a periodic table and look at it. You should pause the video and solve this one here. I'm going to pause the video now. I'm going to give you 3 seconds. 3, 2, 1. Alright, welcome back if you pause the video. So, what's the formal charge here? Well, we know we have a hydrogen here. We have a bond here, so it's 2, 4, 6, 8. 1, 2, 3, 4, 5. So it's going to be 5. And then oxygen has 6. Ooh, whoa. That is, oh, we messed up over here. That's going to be 4 minus 5. Oh, no. Sorry. Ha! Right here, I didn't look at the periodic table. It's 5, so that's -1. Whoopsie daisy. Alright, so it's going to be -1. So we have 2, 4, 6, 8. That's going to be 6. 1, 2, 3, 4, 5. That's going to be 6 minus 5. This is 1. This here's 1. Alright, now that we've done that, we should move on. So, now that we've done formal charge and we know how to do it, let's go ahead and do no. No. Ah, what is happening? What? What? No, stop. Okay, there we go. Alright. Now that that's done. Sorry about that, we had some technical difficulties. So let's do isomers. More specifically, constitutional isomers. And actually, I should quickly explain what a wedge and a dash is. A wedge and a dash is literally just the way it's facing. A wedge, actually, I'll show that in the next tutorial. Okay, so let's do an isomer. What is the isomer of? Suppose we said, what's the isomer of? Oh. What's the isomer of something that looks like fat? Oh, it's been so long since I've done an isomer. Okay, what is the isomer of this? Now, what is an isomer? An isomer is basically a different way of writing the same chemical. So we can look at this chemical and say, all right, how can we write this differently? Well, let's start by looking at it. And where can we move the oxygen? Well, we can move the oxygen over here, so that's one isomer. Because that's pretty much the same thing as saying that. Right, so we can move the oxygen over there, and we can move it here and there, right? Now what we can do is we can move that guy over there. So, we move this guy over here. Because remember, end is the same as end, this is the same as this is the same as, suppose you get another one there, it'd be the same thing as that. So we have that, and we can draw another isomer where we'd have this here and this over here, and that's basically our isomer. So that's an isomer. You might want to check me on that. I'm not like 2000% certain because honestly, when I did isomers, it was so easy I just completely forgot it. Yeah, anyways. Alright, so thank you for squids for watching. In the next organic chemistry video, I'm going to be doing hydrogen deficiencies and I think chirality. I think I'll do some chirality with conjugating Zenomon and RNS configurations. Alright, and yeah, thank you all for watching, and I'll see you in the next tutorial. Adios.